This video will be on section 2.7, marginal analysis in business. It sounds kind of scary, but what we'll really see here in this section, marginal means do the derivative. And the first little section is talking about marginal cost, revenue, and profit. And then the second half of the section will be introducing average and then mixing in average with the marginal functions. And I'll be able to kind of explain in words why the average, and especially the marginal average functions, are so much more meaningful than just the marginal cost, revenue, and profit. Right, so if you're not super familiar with the cost, revenue, and profit, what they mean, I'll just kind of outline them very, very briefly. Cost is how much, I'll say C of X, the cost of producing X items. So, whatever you're making, if it's shirts, C of 10 would be the cost of producing 10 shirts. R of X, the revenue, is how much money you bring in. So revenue, which is the money brought in, from selling X items. Right, and then the profit, P of X, is the profit, which is how much money you make, how much you actually get to put in your pocket, which is of producing X items, I should specify. And the way you figure out profit, usually you're not going to be given it, sometimes you might be, but profit is revenue minus cost. Right, so if you bring in $100, maybe you sell your 10 shirts for $10 each, and they cost you $2 each to make roughly, then R of 10 would be 100, C of 10 would be 20, and your profit would be 100 minus 20, which is 80. Right, so that's just a very brief rundown of what those mean if you're not familiar with it. The marginal functions, the corresponding marginal functions just mean the derivative. All right, so marginal, once again, really, it's just asking you to find the derivative because you might be asked in words, find the marginal cost. It might give you the symbol, in which case, it's just the symbol from last section, the last couple sections. And same thing for revenue and profit. Right, so like I said, it's just a double reminder here. In many practical applications, the interest is on the profit function, but you will only be able to calculate the cost and revenue. So like I mentioned, simply note here that profit is revenue minus cost. All right, so the first one here, it says compute C prime of X if C of X is 175 plus 0.8X. So we want to do the derivative. Right, so C prime of X, we do the derivative of each part. So we do the derivative of 175 plus the derivative of 0.8x. And the derivative of a number is 0. Right, just one more reminder on that from last section. Derivative of a number is 0. And then the second one is also one of our special rules. The derivative of a number times x is the number. So the derivative of 0.8x, carry our plus through, is 0.8. And then if you just add these two numbers together, you see we actually do get a number for our answer here, which is fine, it's 0.8. If you think about it, this kind of makes sense though, because if we graph this thing, this is actually a line, y equals mx plus b, and the slope is 0.8, which is exactly what the derivative is telling us. Right, so the second one says find the marginal revenue, so do the derivative. R prime of x is what we want. If the revenue is given by x times 23 minus 0.02x. Now, one important thing to point out here, we don't have a derivative rule for multiplication. We have x times this, 23 minus 0.02x. So the question is, how can we do it? If we don't know how to do the derivatives with multiplication, well, you can get rid of the multiplication by distributing the x through. Right, that's the problem here. We don't know how to do derivative with multiplication. We can get rid of the multiplication by distributing. Which is exactly what I'm going to do here. So I'm going to distribute first and then do the derivative, right? So I'm not changing the problem yet. I'm not doing the derivative at all. I'm just getting rid of the multiplication. That's why I'm rewriting it as r of x. X times 23 is 23x minus x times 0.02x is 0.02x squared. And then we want to do the derivative of this. All right, this has no multiplications. We can do the derivative of this. All right, so let's do the derivative of 23x minus 0.02x squared. Do the derivative of each part. Oops, forgot that. 0.02x squared. Bring the numbers out front, so we bring the 23 out front. Actually, this first one here is our special rule again, right? We've got just a number times x, so the derivative of that is just that number. And then minus, for the next one here, since we have a power on x squared, we're going to have to use the power rule. We bring the number out front, 0.02 times the derivative of x squared, and the derivative of x squared we can do the power rule on and finish it up. We got 23 minus 0.02 derivative of x squared. We bring the 2 down, rewrite our x, subtract 1 from the power, and then simplify. All right, we can't combine these. The 23 is by itself. 0.02 times 2 is 0.04. X to the 1 is just x, and that is our marginal revenue function. All right, once again, don't try to use a shortcut to compare this to the very beginning, because I could change this x to an x squared and you can still distribute through, and we can change the inside quite a bit as well. Really what you want to make sure you're doing is following and understanding. Last section we didn't have any problems where you had to multiply by distributing to get rid of it, but we introduced that idea in this section. Before I move on, one thing that I like to mention that's important is that we will eventually have a rule for multiplication, but this way that we did it is easier than the multiplication way. So if you can easily distribute something, you should do it that way. All right, so the last thing here is find the marginal profit function. So we want p prime of x, and it gives us the cost and revenue. The cost is 223 plus 0.8x, and the revenue is 9x minus 0.3x squared. Right, there's two ways you can do this. Since profit is revenue minus cost, like I said, you can do this two ways. You can figure out the derivative of each and then subtract them, or subtract them, the original ones, and do the derivative of that. And I honestly like to subtract them first. But if you do it the other way first, meaning do the derivative of this and do the derivative of this and then subtract them in the correct order, revenue minus cost derivatives, you'll get the same thing. So R of x minus C of x is our profit. R of x is 9x minus 0.03x squared. I like to put parentheses around things when I subtract them. You don't need it in the front for sure, but you definitely need to put it in the back. So the cost 0.8x and 223. If you forget this minus sign, then you'll forget to distribute and simplify. So distribute that minus sign. If you forget the parentheses, it's like when we did the definition of the derivative using the limit. If you miss that minus sign with the parentheses, then you'll get the wrong answer. Right, so then we got minus 223, and then the minus to the 0.8x. And then if you can combine any like terms, which we can, let's do that. I like to put the biggest power of x in the front, even if we do have that minus sign. So negative 0.03x squared. 9x minus 0.8x is 8.2x. And then we got our minus 223. All right, so this is our simplified profit function. And whenever you have to do a derivative, simplifying first is very, very important. It makes it a lot easier. So we simplified it first, then we do the derivative. You know, there was really nothing stopping me from doing it from here or even here. But if you do it, the derivative from this, it's easier without a doubt. So now the derivative p prime of x, we do the derivative of each part. Let me not reuse that color. And then for the first one, we have to bring out the negative 0.03. And it would help if I wrote what's left on the inside, which is x squared. Then the second one here, this is one of our special rules. The derivative of a number times x is the number, minus the derivative of a number is 0. Right? And now, after we do the derivative of x squared, we just simplify and we're done. The derivative of x squared, we bring the 2 down, so we get 2. Rewrite the x, the power becomes 1. We subtract 1 off, and then we have plus 8.2. Sorry, I ran out of room. Should have used this room, but I don't want to go back over here and make it confusing. And then we simplify negative 0.03 times 2 is negative 0.06x plus 8.2. And that is our marginal profit function for this problem. Right, so the next little section here, it's kind of useful. It shows you how powerful the derivative is. And I have kind of an example worded out. So one important use of marginal functions is using it to approximate the cost of producing some particular item. All right, let's say you want to know you have some product. Let's just go back to the shirts again, and then your shirts, the cost is variable. It's a function of x, and you want to see how it's changing. So how much does the 100th shirt cost to produce? Your first one might cost $100 because you have that startup, but then by the 100th one, it might only cost you like $2 or something. But you want to know right away without having to sell 100 shirts and then subtract off, without producing 100 shirts. You just want to know in the future, how much is it going to cost? Well, what we could do is rewrite the cost of the 100th item. Right, so the 100th item is the C of 100 is the cost to produce 100 items. C of 99 is the cost to produce 99 items. And if you subtract them, what you're left with is the cost to produce only the 100th item. Right, so once again, you can think about it, in very, very simple terms. Let's say, this is what just popped into my head, but let's say you need to buy, you want to buy 100 apples for some reason at the store. So you have 100 apples, but you want to know how much the 100th weighs, and for some reason you can't just take it out. Right, once again, just kind of visualizing you have a box with 100 apples in it, and then you want to see how much it weighs. One way to do that would be weigh the box of 100 and then take out the 100th apple and then weigh the cost of the 99th. So let's say 100 apples weighs 50 pounds and the 99 apples weighs 49 pounds, then your 100th apple weighed 1 pound, which would be a very big one. And then the reason why I have 100 minus 99 on the bottom is because of the definition of the derivative, but this is just 1. But if you go through and rewrite some stuff, what it tells you is that the cost of the 100th item is just the derivative of the 99th item. And this was just a very, very specific example. I could have changed the 100 to 10, and what would happen over here is we would do the derivative of the 9th item. All right, so we get the following formula, which we'll see is very useful because in general, it's easier to do a derivative and plug in a number than do this messiness. So it says the cost of the nth item is about the derivative when we plug in 1 less. So all right, so we'll actually do this with an example. That way it'll make more sense than my example of weighing apples. All right, so here it says the total cost in dollars of producing X food processors is given by this function. C of X equals 1500 plus 80X minus 0.2X squared. So the first thing says find the exact cost of producing the 21st food processor. Well, in order to figure that out, just like I outlined above, C of 21, this gives us the amount to produce all 21. But we don't want all 21, we just want the 21st, so we have to subtract off C of 20, which is the cost or the amount to produce for the first 20. Right, so once again, it's like kind of like we're weighing the 21, and then we're taking the 21st out, and then we're weighing the 20th. And the difference is how much the 21st one weighs. Right, but this has nothing to do with the derivative because it says the exact cost. But what we do is evaluate this. We do C of 21. We plug a 21 into C of x. And then we subtract, and then we plug in 20. Once again, when you subtract off, because you have all this plus and minuses, make sure you use parentheses. All right, so that first thing is our C of 21. And the second part is our C of 20. And since these numbers are rather messy and a little large, nothing wrong with using your calculator here. So C of 21, I'm going to do one part at a time. We got 1500 plus 80 times 21 minus 0.2 times 21 squared. And we want the exact cost, so use the entire decimal here. We get 3091.8 minus, and now we want the C of 20. So you can type this whole thing in. If you have the TI-83 or 8040, you can hit second enter. It'll bring back up what you just typed in, and I'll replace the 21s with 20s just to make it easier on myself. And we get 3020. Whoops, button here. And then subtract those off. Actually, you can do it in our head. We got 71.8. Since we're dealing with money here, if you want to write it, with 2 decimal spots, that's fine. All right, so that's one way to do it. Now, because you are still relatively new at derivatives, maybe doing the derivative of this isn't super quick, but once you get a lot of practice in, doing the derivative of this and plugging it in is a lot quicker than actually doing this. It's also much quicker for computers. So we want to use the marginal cost to approximate the 21st item. So here's the main thing. We want to do the derivative, but we don't plug in 21, we plug in 20. We plug in one less. So we want to compute C prime of 20, one less than 21. All right, so you need C prime of x first. Like we mentioned in the previous section, you have to do C prime of x, you got to do the derivative and then plug in a number. If you plug in 20, then you're going to get a number. And then when you do the derivative of the number, it's always 0. So that's why you got to do the derivative first. All right, now we do the derivative of each part of our cost function here. The derivative of 1500 plus the derivative of 80x. And if you're already comfortable doing this, in your head, you already see what the entire derivative is. That's great. The derivative of a number is 0. The derivative of a number times x is the number. And then you may have also noticed the pattern when you do the derivative of something like this. We're going to bring the power down. So we're going to multiply the 2 to the 0.2 to get 0.4 x, and then one less power to the 1 power. But since it's just the first power, I'm not going to rewrite the invisible first power. Right, but it's just the derivative like with the power rule from before. 0.2 times 2x to the 1 power. Saving myself a little room. Right. And then you can simplify the 0 here, but since we want C prime of 20, just ignore it. So we plug in 20 for x here. We got 0, which is irrelevant, plus 80 minus 0.4 times 20. 0.4 times 20 is 8. We get 80 minus 8, which is 72. Right, and that's really close to the answer we got for the exact. This is an approximation. It says the 21st food processor will cost approximately $72. Right, but you can see how much quicker it is. In fact, the messier the equations get here, the quicker it is, because the derivative is usually much quicker to do than plug in twice. And the derivative also makes less terms. You notice how we went from 3 terms here to 2 terms, because the 0 is not important. All right, so that's one way you can use derivatives to help yourself out. Oddly enough, if you figured out the exact cost, what I mentioned before, the exact cost of producing 0 items, so just like your startup cost, is this 1,500. So it changes a lot as you go on. How much does each one cost? And in general, the more you produce for a product, the less it should cost. If it's going up, then that means you're probably doing something wrong. All right, so often knowing information about functions and their derivatives are not enough. What is of interest is how to find the average function changes, since you really want to make sure your items are getting cheaper or more profitable on average. Okay. So your cost is always going to go up, right? Because it should cost more to produce, for example, 100 items than 99 because you're doing more. But what about the average cost? You would want the average cost to go down. The harder you work, the more you hope to make money. So your cost should be going down. You'd also hope that your average revenue goes up, although I think that's a little less realistic. But that should stay the same, and then your average profit, you want to go up. So the way we compute average functions is we divide them by x. Right? And we use this bar to represent average, but that's not something I require you to remember. So this C bar of x means the average cost. All right, and revenue and profit are exactly the same ideas. And it looks like I forgot to leave enough room here, but good thing we won't need much room for this. It says find the average cost function if cost and revenue are given by C of x equals 175 plus 5.4x and R of x equals 2x minus 0.5x squared. Now, if you're reading this, it might throw you a little through a loop because they're giving you more than you need. To find the average cost, all we need to do is take the cost function, our formula, and divide it by x. We don't need this at all. The R of x is just unnecessary. So they're just trying to throw you off, give you too much information. And in real life, you're gonna, for problems, you're gonna have a lot of information. You need to pick what's relevant and what's not. All right, so the average cost function, C of x over x, equals 175 plus the 5.4x, our cost function, divided by x. Now you can actually stop here, but I would simplify this by breaking it down into 2 fractions. The reason is the next little section, we're going to be doing the derivatives of these, and we can't have fractions like this, so we're going to need to simplify anyway. All right, so to break it into two fractions, really what I'm saying is undo what you would normally do when you find a common denominator. We put each part over the denominator. It's 175 over x and the 5.4 x over x. Okay. And once again, you can kind of stop here, but especially in the second term, you can simplify it. You can cancel the x's out. But also, one thing that you're going to want to do in the next section, when we do the derivatives, we know we can't do the derivative if x is on the bottom, so we can bring it up to the top. And we know when we bring it to the top, what we got to do is change the sign on the exponent. Since it's just x, it's really x to the 1 power. When we bring it to the top, we change the sign on the exponent. So it becomes x to negative 1 power. We're not moving the 175. You're only moving the x up. And the back thing is only 5.4. Right, so we've seen this rule a couple of times now, and you'll see it quite a bit throughout the class. You change the sign of the exponent when you want to bring the thing up. Also, if for some reason you want to bring it down, you would change the sign back, but we don't want to do that here. All right, so this is the absolutely simplified average cost function. Like I said, this over here isn't wrong, but if when we get to the next section, we want to do the derivative of this, you have to have it written like this. Otherwise, you can't do it yet. Right, so like I said, the average cost function does not really tell you that much because you want to see how it's changing. Right, so knowing that the average cost, let's go back to our shirt example. Let's say the average cost of producing 100 shirts is $8. Well, that's great, but is it going up or down? Right, we want it to be going down. So that means when we study rate of change, we do the derivative of the average cost in that case. And those are called the marginal average functions. So the marginal average cost function, the notation is terrible because we have the bar with the prime here, is defined to be the derivative of the average cost function. The marginal average revenue and profit are similar. One thing that's really important, since you have both words here, it's easy to ask the question, should we do the derivative first and then do the average, or do we do the average first and then do the derivative? But like I mentioned above, we want to do the derivative of the average because that's what's important. So we do the average first, then do the derivative to find the marginal average functions. All right, so once again, this can definitely be the most confusing thing that we've done, at least in the past couple sections, because you have two words here. Just make sure that you do them in the correct order. We do average, then marginal. Although it seems like, reading left to right, we should do it the opposite way. So do average first, divide by x, then do the derivative of that. All right, so I just have one word problem here. It doesn't matter if it's asking for cost, revenue, or profit. You would do them the same way because you have to be given the functions. This says the total cost in dollars of manufacturing X auto body frames is given by 70,000 plus 200X. So I like to give things names even though you don't need to here because it's telling you the total cost. We got C of X equals 70,000 plus 200X. Right, the first part says find the average cost per unit if 250 body frames are produced, and then interpret the results. Right, so let's do the average. This is not the marginal average, it's just the average. So we want to do C of x over x. Our C of x is 70,000 plus 200x over x. And I'm going to simplify it just like last time. So we break it up into our two fractions. I don't usually like to write the commas in numbers when I'm working them because I might get confused. It might start to look like a stray mark. It might look like a minus or multiplication if I make it look messy. So I don't usually write them in. All right, but we can simplify, break it up into the fraction. I guess I didn't super explain this, but although it is definitely prerequisite knowledge, but think about if you were going from this side back over here. Since we have a common denominator, this is exactly what you would get. We're just breaking it apart. Now to simplify, we can cancel the x's out, and then we want to bring this x up. And just like last time, the power on here is 1, so when we bring it up, it will become -1. So we get 70,000 x to the -1 power plus 200. That is the average, simplified average cost function. Now we're not done in this problem because we want it if 250 frames are produced. So now we want to plug in x equals 250 to the average. Figure that out. We got 70,000 times 250 to the -1 power plus 200. And then you can type this in your calculator. So 70,000 times 250 raised to the -1 power plus 200. Your calculator can deal with negative exponents just fine. That's why it's okay. We got 480. Right, so the average cost per unit if 250 frames are produced is 480. So to interpret these results, what we would say is that pretty much exactly that the average cost to produce a body frame, something like this, when 250 are produced, is 480. We'll just assume there, it does say in dollars, $480. Right? This has nothing to do with derivatives, so it's not telling us the rate of change at all. Now, the second part here, it says find the marginal average cost at a production level of 250. Interpret the results. All right, so we want to do the derivative of the average. Now, since we did the average in the previous step and we simplified it, we're going to do the derivative of this. Then plug in 250. All right, so we want to do the derivative of the average, and the average function the average cost was 70,000 x to the -1 plus 200. If you take the time to figure out the average cost and simplify it, use the simplified version. Do the derivative of each part. Now leave that in range for a second. Now we do the derivative of each part. The 70,000, we know it's going to come out front, so it'll stay around. Then the derivative of x to the -1, we have -1, bring the power down, x, subtract 1 from the power is -2, plus the derivative of 200, which is 0. Now, even though we're going to plug this in our calculator and get a number, I like to just simplify it a little bit because it's pretty messy. Negative 1 times 70,000 is negative 70,000 x to the negative 2 power. All right, so this is the marginal average cost. Right, once again, if you simplify the average cost whenever you do it, then the marginal average cost is a lot easier. If you leave it here, then doing the derivative of this, the first couple steps are just doing this part anyway. So I'd recommend just practicing simplifying from the get-go. All right, now we're going to plug in the 250 to our marginal average function. We got negative 70,000 times 250 squared. Oh, to the negative 2 power, not squared. And then plug that in. Negative 70,000 times 250 to the negative 2. Forgot the negative. And we get negative 1.12. All right, so we can interpret this just like last time, except now we're talking about the derivative, so it's a rate of change. So what it's saying is the rate of change of the average cost at a production level of 250 body frames is decreasing. Since it's negative, it's decreasing by $1.12. Right, now that might not seem like a lot, but that's the average. So think about it. If you produce 250 and then you want to make the next one, your average cost is going to go down by this much. But since you're already at 250, think about multiplying this number by 250. That's really how much it's going down. All right, this is a huge number in comparison to how much it costs. Now, if the average one costs like $1 million, this would be almost nothing. This would be worthless in a grand sense of things. Okay. Right. But that's why the average cost is so important, is it tells you, really you need this to be going down, and how much is it going down is also important. All right, part C is to use the results from part A and B to estimate the average cost per frame if 251 frames are produced. Now, if you use the interpretation, this is actually pretty straightforward. The average cost at 250 is $480 and decreasing. This is from part A, and the part B says it's decreasing by $1.12. So our answer, if it's decreasing by $1.12, then all we do is we do 480 minus 112 equals, let's see what it is. Just don't want to mess up the decimal since we've gotten this far. We have $478.88. Okay, and that's really all there is to that. Now, maybe I got lucky when I looked at the question and it only asked me for 251, which is one more than 250. So let's pretend, I don't think there's another part here. Let's say if we wanted to know or to estimate the average cost if 255 frames are produced. Now, there's not much more to this, but all you do is take the average cost at 250 And since we're going to go up by 5 from 250 to 255, what we do is we take our 480 and we subtract off the 112. That's telling us how much it costs to produce one more, times 5. Right, so to kind of think about it once again, derivative is sort of like slope. If we go up, if we increase our x by 5, we should multiply the change by 5 as well. Right, so 480 minus 112 times 5. 112 times 5 is 5.6. And 480 times 5.6 is 474.4. And if we're talking about money here, you can add the 0 in at the end. Typically, when it comes to estimating things with derivatives, we don't like to go very far away. So I wouldn't want to estimate 500 because I will guarantee you that will be way off. It's way too far. We wouldn't want to go away more than a couple. So whatever you might ask to do here in part C is probably very close to the original one. But I just wanted to mention that in case not everyone has just one away.